Let's consider our primary result for this section. So this theorem says that if we have two finite dimensional vector spaces V and W, then V is going to be isomorphic to W if and only if the dimension of V and the dimension of W are equal. Okay. Now we have discussed finite dimensional vector spaces before. There are some infinite dimensional vector spaces, but primarily in this class, we will mostly be focused on finite dimensional vector spaces. Infinite dimensional vector spaces behave a little differently in some situations. Okay, but if we do have finite dimensional vector spaces, then we know that those vector spaces will be isomorphic if and only if they have the same dimension, right? Let's go ahead and prove this result. And this proof will be a little bit lengthy, but it is an important result, all right? So notice we actually almost have two proofs here. If and only if means that if V is isomorphic to W, then the dimensions are equal. Okay, we call that the only if direction. And if the dimensions are equal, then the vector spaces are isomorphic. That's the if direction. We need to prove both directions. We need to prove if one is true, then the other is true, and vice versa. All right. So let's start with the only if direction. Assume V is isomorphic to W. Suppose because V is a finite dimensional vector space, we could suppose that the dimension of V is finite, say equal to n, with basis V1 to Vn. Okay, so n vectors in the basis. Remember, the dimension of a vector space is the number of vectors in its basis. All right. What we want to find is a candidate basis for W that has the same dimension. Okay. So specifically, we want, let's say we will show that actually, I need to define one thing first. I apologize. We know V is isomorphic to W. So let's let T be a linear transformation from V to W. Let's let this be an isomorphism. So it is a invertible linear transformation. Okay? It doesn't really matter which one. Generally, for any two vector spaces, there's going to be multiple possible isomorphisms between them. If any one exists, then they are isomorphic. Okay? We will show that the transformation of the basis of vector space B is going to be a basis for vector space W. Okay, and I probably should say here that this is a basis for vector space V. Okay. So what two things do a basis have? We will show, whoops, helps if I write everything right. We will show that this set of vectors is a basis for vector space W. Okay. So we want to show this is a basis. What two things do a basis do? A basis spans the vector space, and it and the vectors are linearly independent, right? We need to show those two things. We're going to use the fact that we have an isomorphism. T is an isomorphism. That means that T is an invertible linear transformation. Remember, an invertible linear transformation is going to be one-to-one and onto. Those are going to be two very important properties. All right? First, observe span of these vectors, tv1 to tvn, is equal to vector space W. To see this, take any vector W in vector space W. Because T is onto, T is an onto function because it's invertible. An isomorphism is an invertible linear transformation, and every invertible linear transformation is one-to-one and onto. Because T is onto, there is a vector V in vector space V, so that the transformation of V is equal to vector W. Okay? But vector V is in vector space V, and therefore can be expressed as a linear combination of the basis vectors V1 to Vn. Because V1 to Vn is a basis. And every vector in a vector space can be expressed as a linear combination of the basis vectors. Okay, now what we want to do is we want to show, hey, since the V can be expressed as a linear combination of the vectors V1 to Vn, then W can also be expressed as a linear combination of these vectors. To do that, we're going to take the linear transformation of both sides. Then W, which is equal to T of V, right? Remember, that's how we've decided to choose a relationship between V and W, which is also equal to, here I'm going to substitute out V for the linear combination of the basis vectors V1 to Vn. So substitute out V for A1, V1, plus dot, 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 A and Vn. Now what I'm going to do, I'm going to use the fact that T is a linear transformation. And so I can break up the sum, I can pull out the scalars. Okay, and so what I've shown is that vector W can be expressed as a linear combination of the vectors tv1 all the way to tvn. Okay, now there was nothing special about vector W. I just said take any vector W in vector space W. And so since W could be any vector, that means every vector in vector space W must be able to be expressed as a linear combination of the vectors tv1 to tvn. And that means that these vectors must span vector space W. Okay, so that's property one. The vectors need to span vector space W in order to be a basis. Property two, they need to be linearly independent. Okay? Next, we will show the vectors tv1 to tvn are linearly independent. Okay, so to show these are linearly independent, remember a set of vectors are linearly independent if when I look at a linear combination of them and set them equal to the zero vector, the only way that I can make that work is with a trivial solution, setting all the coefficients equal to zero. So consider the homogeneous linear combination equation let's go b1 tv1 plus plus bn tvn equals 0, equals the zero vector. I want to show that the only choice of coefficients here is having them all be 0. Okay, now for this we are going to use the fact that the linear transformation is an isomorphism and therefore 1-to-1. Because it's an isomorphism is just an invertible linear transformation, it is going to be a 1-to-1 transformation. All right? So I'm going to use the fact that this is a linear transformation next. I'm going to kind of put everything back together. b1 v1 plus plus bn vn. Okay, combining the linear combination, putting it all inside the transformation. Okay, so the transformation of this single vector must equal to 0, the 0 vector, right? But t is 1-to-1. So there's only one choice of input into t that I could plug in to give me the 0 vector. And if you know about linear transformations, you know that always the transformation, the linear transformation of a 0 vector is going to give me the 0 vector. Okay? What that means is that this, the inside of the transformation, must be the 0 vector. We have that that b1 v1 to bn vn, this sum, this linear combination, is equal to the 0 vector because the inside of this transformation, both give me the same output. Since the transformation is 1-to-1, the inputs have to be the same. This has to equal that. Okay? But now we're using vectors v1 to vn. We know by our assumption vectors v1 to vn is a basis for vector space V. And a basis is linearly independent. So since the vectors v1 to vn are linearly independent, it follows that b1, all the b's must be equal to 0, right? These vectors are linearly independent, and so the coefficients must be the trivial solution. But these are the same coefficients that we had with our original linear combination equation up here. And so b1 to bn must be equal to 0 here too, which means that we have only the trivial solution. So thus, the vectors must be linearly independent. Okay, so we proved the two things we really needed to prove here. We've showed that these vectors span the entire codomain W, and that set of vectors is linearly independent. So that means the set of vectors is a basis for W. Okay. If it is a basis for W, that means the number of vectors we have here is going to be the dimension of W. And you could see here, here's the first vector, and then there's a lot of vectors that I'm not showing. But then here's the last vector. The last vector is the nth vector. And so the dimension of the vector space is n. Thus, let me use actually a different word. I used thus up here already. Therefore, dimension of vector space W is equal to n, which is exactly what we assumed at the beginning the dimension of V was equal to. All right. Okay, so that's one down. Okay, I know it's a lot. We've proved this direction. We've shown that if V is isomorphic to vector space W, then the dimension of V and the dimension of W must be equal as long as they're finite dimensional vector spaces. All right, now we need to go the other direction. So for this other direction, we're going to start by assuming that the dimension of V and the dimension of W are equal. Then we need to show that the vector spaces are isomorphic. Okay? So now we're going this direction. Assume that the dimension of V and the dimension of W are equal. Let's say they both equal to n. Right? That means they both have bases of n vectors. So let's let V1 to Vn be a basis for vector space V. And let the set W1 to Wn be a basis for vector space W. We know these bases exist. I don't really care which one it is. Generally, a vector space will have multiple possible bases to choose from. We just pick one of them. Doesn't matter which one. We know there's some basis out there of n vectors that we could choose for V that we could choose for W. Okay? What we need to do is show that V and W are isomorphic. That means there's going to be a linear transformation that goes from one to the other that is invertible. Right? So we want to define such a linear transformation. So let's let T, which maps vector V to vector W, be the linear transformation. Such that T of Vi is equal to Wi for each I. Okay, here each I, of course, being from 1 to n, the possible values, the possible subscripts. Okay, so V1, the transformation of V1 will go to W1, the transformation of Vn will go to Wn, and so on. Okay, this is a linear transformation, and it's pretty straightforward to prove that. What we want to show is that this isn't just any transformation, but linear transformation, but this is an invertible linear transformation. To show it's invertible, we need to show the transformation is 1 to 1 and that it is onto. So to show T is an isomorphism, we must show T is 1 to 1 and onto. Okay, if t is 1 to 1 and onto, then it is an invertible linear transformation. And an invertible linear transformation is exactly what an isomorphism is. An isomorphism is just a fancy way to say an invertible linear transformation. Okay? All right, so let's start with 1 to 1. Suppose we have two vectors in V. And that their transformation gives me the same value. So the transformation of u1 and the transformation of u2 are equal to each other. What I want to show is that, hey, if this is true, then actually u1 and u2 have to be the same value. In other words, there's actually only one value that gives me the transformation of vector u1. All right? There's only one value that is equal to, that gives me that output. All right, what we're going to do is we're going to use the fact that we have a basis in vector space V, V1 to Vn. We know that U1 can be expressed as a linear combination of the basis vectors in vector space V. So A1 V1 plus AN VN, all the V's in the middle, okay? And similarly for U2. Different coefficients potentially, but we know that any vector in vector space V can be expressed as a linear combination of the basis vectors of vector space V. Actually, let me write for some coefficients. Okay. Okay, so we know that T of U1 and T of U2 are equal. We assume that, right? What I'm going to do is I'm going to subtract U2 to the other side so that we have 0, the 0 vector on the right-hand side. Okay, we love having 0 on one side of the equation. And now I'm going to use the fact that T is a linear transformation and combine the two linear transformations into a single linear transformation. All right? But since, oh, actually, hold up. Now what I'm going to do is I'm going to plug in what we know U1 and U2 to be. So U1 is A1 V1 all the way to AN VN, right? Expressing U1 as a linear combination of those vectors. And U2, B1 V1 plus dot 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 plus BN VN equals 0. I'm sorry, I made a little mistake here. This is right, but it's a little extra. Let me start from here. Plug in the linear combinations from here. A1 V1 plus dot 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 plus AN VN. So that's T of U1 becomes this minus transformation of B1 V1 plus dot 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 plus BN VN equals 0. And here T of U2 is equal to this. We just substituted out U2 for its linear combination in terms of the basis vectors for vector space V, right? just swapping out u1 for its linear combination and u2 for its linear combination. All right. Now we use the linearity of t, and we're actually going to break this apart. So I'm going to get a1 transformation of v1 plus plus an transformation of vn minus b1 transformation of v1 plus plus bn transformation of vn equals 0. Okay, but transformation of v1, transformation of v2, transformation of vn, remember we defined those. We defined our transformation t so that the transformation of vi is equal to wi, the vector in the basis for vector space w. So I can substitute out tv1 for w1 and all the other t's for the appropriate vector in the basis of vector space w. So tv1 is w1 and tvn is wn. Okay? And now what we're going to do, we're just going to combine like terms. So a1 w1 minus b1 w1, I can combine their like terms. I get a1 minus b1 w1. And I'm going to keep on doing that until I get to the last term, an wn and bn wn. Combine those terms, I get an minus bn wn equals the 0 vector. Okay? But now we're going to use the fact that w1, w2, all the way to wn, that's a basis for vector space w, and so therefore these vectors are linearly independent. And so this homogeneous linear combination equation only has one solution, namely the trivial solution, where a1 minus b1 and an minus bn on all the other coefficients are equal to 0. But since w1 to wn is a linearly independent set, because it's a basis, ai minus bi equals 0 for each I, which implies that ai is equal to bi. How do we get ai and bi again? They're the coefficients of these linear combinations, and I'm just seeing a little error here. This should be b1 and v1. Okay, they're the coefficients of these linear combinations, right? So u1 is equal to a1 v1 plus plus an vn, but a1 is equal to b1. And all the other a's are equal to the corresponding b's. an is going to be equal to bn. And this is exactly what vector u2 is equal to. All right? So we have showed that, hey, if the transformation of two vectors are equal, then those two vectors that we plugged in actually have to be the same vector. They have to be equal. And that's the exact condition that shows that T is a one-to-one transformation. Okay, all right, one more condition left. We need to show that T is an onto transformation. So finally, let vector W in vector space W be arbitrary. Now we have a basis for vector space W. So then W is equal to, say then for scalars C1 to Cn, W is equal to C1W1 plus C2W2, and actually let me just go to the end, CNWN. Okay, just using the fact that W1 to Wn is a basis. And so therefore the W1 to Wn span all of vector space W, and therefore there's a linear combination of those vectors that give me vector W. Okay, with coefficients in this case, let's call them C1 to Cn. All right, but W1, Wn, all the other W's, we defined our linear transformation T so that each Wi is equal to the transformation on vector Vi, where vector Vi is from the basis for vector space V. So I can say that I can swap out W1 for T of V1 and Wn for T of Vn, and then use the properties of and the fact that T is a linear transformation to combine this into a single transformation, C1 V1 plus dot 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 plus Cn Vn. Okay, which means there is some vector in V that I could plug into the transformation to get W, right? C1 V1 plus dot 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 plus Cn Vn, that is a vector in V. Because V is a vector space and therefore closed under vector addition and scalar multiplication. So if I scalar multiply these vectors, add them together, I'm still in vector space V. Okay, so if I'm plugging something in vector space V in and getting vector space W, that means the transformation is onto. Because there was nothing special about vector W. The only thing special about vector W is it was in vector space W. And so any vector in the vector space, this holds true for. Okay, and if it's true for any vector in the vector space, that means transformation T is onto. I can map some vector in vector space V onto every other vector in vector space W. All right, so we've shown that T is 1-to-1. We have shown that it is onto. Those are the two conditions we need for T to be an invertible transformation. And thus T is an isomorphism. Remember, an invertible linear transformation, I should say linear here. An invertible linear transformation is an isomorphism. That's the definition. And if T is an isomorphism, that means V and W are isomorphic to each other. And so that proves it. Okay, I know it was a lot, but we've proved a very critical result here. If we have two isomorphic vectors, they're going to be, two isomorphic vector spaces. They're isomorphic if and only if their dimensions are equal, if they're finite dimensional. Okay, if their dimensions are equal, they're isomorphic vector spaces. So the only thing you need to check from now on to determine if two finite dimensional vector spaces are isomorphic, check to see if they have the same dimension.